Okay, hi everybody. In this video, I'm going to talk about the solutions to Exam 2 for Fall 2023 ITCS-3145 Parallel Computing. We're just going to go through it pretty quickly and discuss the solutions, and especially for these early questions, 1 through 7, these are largely questions about your sort of factual understanding. So things like definitions, vocabulary, applying certain concepts like Amdahl's law. If you know Amdahl's law, then there's not much to do there. So that's sort of what's going on. That's what we're going to try to do. And then for the last 3, I'll walk you through the solutions practically. They use the methods from the slides, but we won't take the time to do the slides for those. But for 1 through 7, I'm going to try to show you where you will have studied for them on our website and our slides that we have available. 8 through 10, all of that is there, but also you've had all of these as homework type problems. And so we've walked through a number of them in class. We've gone through them several times. So I'll walk you through the method again, but the details you can find in the slides. So number 1, let's just start there. So what is the difference between concurrency and parallelism? You might remember this is really the first thing we talked about in the shared memory section, or one of the first things that we talked about. We discussed what is parallelism and concurrency, and our TA has done a good job of summing this up right here. Concurrency is when 2 processes can happen in different order relative to each other or independent of each other without changing the outcome. If you have 2 events, A and B on your calendar, and it doesn't matter if you swap them, you swap B for A, then they're concurrent. They have the concurrent property. They can be run concurrently. Parallelism, if you're able to run in parallel, you must be concurrent. And so you can run A and B at the same time. Parallelism is actually doing them at the same time. You can find this in the slides, the very first slide deck that we covered, which is linked. I'll show that in a second. Processes are concurrent when they happen in different order relative to relative to one another. It often needs concurrency control, but that's another detail. Key question here is processes are concurrent when they can happen in a different order relative to one another. Your laundry is not concurrent. If A is wash and B is dry, you probably don't want to dry before you wash. So that would not be concurrent. But if A is do your laundry and B is take out the trash, probably it's okay if you flip them. And probably it's okay if you do one and your roommate does the other one at the same time. That would be concurrent and parallel. Okay, let's look at our exam, or real quick, this slide deck that this is referencing is right here. So all of these topics that you can study are right above the summary for the day that we covered it in class. All right, let's look at exam question 2. We've discussed 4 types of memory dependence relationships in class. Which one does not generate a PTG dependency? If you don't remember what a memory, or you don't know what a memory dependence relationship is, I think your hint is right here. It's something that generates a dependency in a PTG, in a parallel task graph. So if you know what a parallel task graph is, which I hope you do, then something creates these arrows. And apparently there's 4 of those things, but only 3 of them actually create the arrow. And I think you know these. And so we can check this out. The slides are not strictly, or the questions are not strictly in order of the slides like I usually do this time around, just because I moved the longer questions to the end of the exam, hopefully to try to help you with your time. I don't know how well that worked, but anyway, this we covered on October 16th, extracting parallelism. Dependencies. When there's a dependency, you have a flow dependence, read after write, output dependence, write after write, anti-dependence, write after read, and the one that's missing, of course, is read after read. because read after read does not generate a dependency. And so if we go to this extraction slide deck, then we find when is there a dependency from X to Y? In these three cases, read after read does not create a dependency. All right, so next question. Number 3, every multitasking operating system has a thread scheduler. What hardware component does the scheduler map threads to? Keyword hardware component. So we've only talked about so many hardware components. I would argue maybe we've only talked about CPU cores and memory. Which one of those do we think is a worker? Which one can actually do work? Threads are work. Which hardware component can actually do work? If we take a look at our slides, our introduction to shared memory, you might recall we talked about a CPU is made up of cores that contain execution units that can do work, and we map threads to those cores using the scheduler. So the answer to this question, what does the scheduler map threads to? Cores, CPUs. If you said workers, I would take that. If you just couldn't remember the word core, although you really do want to know the word processor, core, CPU, those words. But if you wrote worker, I'd probably give you credit for that. Anything like that. And you'll find that here too on the day that we started talking about these things. There's certainly details in here discussing that a CPU core is a hardware unit. And your code is scheduled, your threads are scheduled by the operating system and run on the hardware. And so that's where this is the link to the slides as well. All right, question number 4. We know code can deadlock if blank. Also, for C code, we can use the tool blank to help diagnose race conditions and deadlocks in our own code. Well, we've only really talked about one guaranteed, definitive, 100% way to determine if there's deadlock. And those would be the Kaufman conditions. And so what could go wrong with mutual exclusion on October 20th? We could deadlock. 4 conditions for deadlock. If you wrote these 4 conditions, okay. It's more than I needed because Kaufman would have done it, but I'll take all 4. That's just as good an answer. So if you wrote all 4, that's totally fine. And this is basically copied and pasted from the slide. We can pull up the slide real quick. If I can find it, we can try to pull it up. But fundamentally, deadlock happens when all Kaufman conditions are true. So we know code deadlocks if all Kaufman conditions are true. What tool can help us was the other part of the question. For C code, we can use the tool blank to help us diagnose race conditions. You might recall this is the same tool that helps us do memory checking, memory error conditions also. Same tool, really the only tool I think we've talked about that is related to C code, besides maybe your compiler, is valgrind. And more specifically, the tool, which you use, the argument tool equals Helgrind, which is, fun fact, it's technically Valgrind, but nobody pronounces it that way, even though that's the correct way. Helgrind is the correct answer. It is the race checker. It will check your code for race conditions, deadlocks, these sorts of things. We spent about 25 minutes doing a demo of that in class, one of these days. And so, if you didn't know any better, and you say, well, what are the tools I know? Well, Valgrind's one of them, and that's a pretty good guess. That's probably your best guess, even if you didn't remember the Helgrind demo. So that can be, those are the 2 answers for number 4. Generally looking for Kaufman conditions and looking for Valgrind or Helgrind as the answers. All right, back to the exam. Number 5, review the following code. Performing a parallel particle simulation. This logic contains a mistake that will limit parallel performance. What is it and why? We start in main. We assume n is the number of particles, t is the number of threads. Maybe that came from command line arguments. Maybe that came from a configuration file. Maybe we made them up. That's fine. It doesn't matter. It says assume. So we're going to assume. And then we're going to allocate a bunch of particles, a particle array, if you will. And then use n as the number of particles, like we said we would. We're going to assume the particles are initialized correctly. We're going to assume a lot of this is correct before we get to the problematic part. Then we're going to allocate a bunch of space for threads. That's legal. And, if I just skip down here, assume cleanup is correct. Oh, okay. Well, we have to assume after is correct too. So something is going to hurt our performance. Mistake will limit our parallel performance. And it looks like it really needs to be right here. I guess it could be right here, but malloc doesn't really have much to do with performance. So, at least not in this scenario. So, probably it's right here. So we create a bunch of threads. We do int I equals 0, I is less than t, I++. And we call pthread create. And we create a thread for each thread we allocated memory for. And then we call pthread join. And this is where the trouble starts. So if you recall talking about pthread join, and that's the kind of question this is. If you don't know what pthread create and pthread join is, you're going to have a really hard time on this question, but you really should know what those things are. We've done 2 assignments with them, etc. So this question is kind of expecting you to know how those behave. Pthread create, when we call pthread create on the main thread, it's going to kind of fork, like we've discussed, and create a second thread, T1, to do work. When you call join immediately after, you're saying, I want to wait for T1 to finish. So you're going to go to sleep. And then eventually T1 is going to finish, and you're going to get to start again, and then you're going to call create. And that's going to fork out here and make T2, and it's going to execute. And what you'll notice is we're not doing anything in parallel. T1 is executing, main thread is asleep. T1 finishes. Main thread creates T2. It goes, the first thread is asleep because we also call join immediately again. And so the performance limiting factor here is that you're joining your threads before you create them all. You're really making this program run sequentially. You're creating another thread and waiting on it. You're not getting any parallel performance. This is going to be slower than the sequential version because you're adding the overhead of making threads without getting any parallelism out of it. So the answer here is you should move the join outside of the loop. You should join much later. You didn't have to write exactly that. If you were able to tell me that joining right after create is the problem, and tell me that's the problem because you're asleep, or you're waiting, or you're joining, something like this, then you get full credit on this question. All right, number 6. Is the below function correct and thread safe? Correct meaning does it clearly do what it's intended to do? You might not have a lot of context for what it's intended to do, but that's not necessary per se for the problem. I mean, it's clearly adding a number to another and printing the result. So let's just go through it line by line. We have a global mutex, that's totally fine. We have a function, that's cool. We assume the threads are going to call this function. We immediately call pthread mutex lock on the global mutex. That's good. That means every thread will share the same mutex. It's bad software engineering, but it's good for correctness. It means every thread is going to use the same mutex. Star A plus equals B, so we're going to add the value of B to the value A points to. And then we're going to print out the results. We're going to print out the new value of A and the original value of B. And then our function is going to exit. And so fundamentally the answer to this question is no. And the answer is because, well, you called mutex lock, but you never called unlock. So is it thread safe? It's hard to say. It is mostly just incorrect Because what happens is if you call this function from 10 threads, one thread will get the lock, and then it will fall out the bottom, still holding the lock, and those 9 threads are going to sit here and wait forever. Unless there's an unlock somewhere else, which is so incredibly unlikely because this is just a bug. So no, it's not correct or thread safe. If you were able to articulate the answer is no, and it's because you never call unlock, then that gets you full credit. All right, so number 7, you have a parallel application where 60% of the code can be parallelized. What is the minimum number of cores required to achieve a 2 times speed up? So this is an Amdahl's law question. We know that our x is going to be 0.4 because that's the sequential time. We know 1 minus x. Our parallel time is going to be 0.6. We can pull up Amdahl's law real quick just to look at the formal definition. So a fraction x of the computation that's serial. So our serial time is 0.4. We were told the parallel time is 0.6. And then Amdahl's law is written like this. The outcome time, let's call it maybe t of n, is equal to x plus 1 minus x over n. Now we know the answer to several of these pieces. We know x and 1 minus x should be 0.4 and 0.6. And actually we know what this is too. Your goal is to get 2 times speed up. So understand, we have here on the left, speed up is just 1 over whatever your time was going to be. So let's say, for example, a very convenient example, we have 1 over t equals 2. If we look back at that's our speed up equation here. If we look back at our exam, 1 over x equals 2. So what we're saying here is we want speed up to be 2. So we have 1 over x equals 2, or 1 over t in this case equals 2. Well, what is t? Well, you can solve this out pretty quickly. You do 1 equals 2t equals 0.5. T equals 0.5. Well, that wasn't proper math, but you get the idea here. You can bring this down. Equals 1, 2.5. 0.5 is the solution here because you divide the 1 over 2 equals. T equals 0.5. That's the proper math. All right, so what that tells us, we want a 2 times speed up. We need 1, we have 2, so we get 0.5. 0.5 is our time, or at least it's our percentage of time. We never plugged in a real time for this problem. So this question just becomes, what is 0.5? How do we get 0.5 out of the rest of this? The only unknown variable is n. So you can go ahead here and subtract out the sequential time from the result time. 0.5 minus 0.4 is 0.1 equals 0.6 over n. N, what divided, 0.6 divided by what is 0.1? Well, if yes, it's decimal math, but ignore the points. 6 divided by what is 0.1? To continue doing the math out just for the sake of argument, 0.1 n equals 0.6. What times 0.1 equals 6? And if we take it further, 0.6 divided by 0.1, we still don't get it yet. It's 6 divided by 1 is going to be 6. This is going to give us 6. So 6 is the answer here. 6 is the n that you plug in. If you take it back and you plug it into the original equation to check your answer, 0.4 plus 0.6 divided by 0.6 is 1, or 0.1. 0.4 plus 0.1 is 0.5. And so that's the solution that you're going to get out of this. So I need to see your work for that. If you got to any point in this that you showed me you knew it was Amdahl's law and you said, oh, of course, it's just going to be 6, then that's fine. And the key here is just not to it's to understand Amdahl's law, but understand the idea is just you're dividing the time you say you can split up by the number of workers you have. That's really the key to this question. The sequential time is fixed. The x is fixed. So your goal is to move it to the left-hand side and focus on what divides this number correctly. Now, we can try this again for the next problem. And let's go ahead and take a look at that real quick. So the next problem asks the same question, but it asks you for a 2.5 times speed up. 2.5 equals, let's take a look real quick and remind ourselves our speed up equation. We're going to try to do the same thing. We're going to try to solve for our unknown here. So speed up on n computational units, our speed up equals 2.5, and we want 1 over x. And so our goal here is what value is going to divide 1 by, or what do you divide 1 by to get 2.5? Well, to get 2, it was 0.5. To get 2.5, well, 0.4 plus 0.4 plus 0.2 is going to get us there. And you can go ahead and follow through on the math and divide this out if you want. And you end up with x equals 1 over 2.5. Point being a whole 0.4, a whole 0.4, and half of a 0.4 is going to give you 1. So your goal here, your outcome goal here, is going to be 0.4. So 0.4 is our goal. So let's go ahead and go back to our equation. 0.4 equals x. X again is still 0.4 plus the remaining time, the parallel time, plus we don't know n, or divided by we don't know n. Now, really quickly getting into this problem, you should see a problem. We're going to subtract the 0.4 over. 0 equals 0.6 over n. What do you divide 0.6 by to get 0? You don't, really. If you multiply n across, n times 0 equals 0.6 is 0 equals 0.6. Oh, that's illegal. We've done something horribly wrong. Or actually, we've done it right, and it just means that mathematically, this is impossible. Well, let's think about it in practice. We're saying, why is it impossible? Well, we're saying we want the total runtime to be 0.4, but the sequential time is already 0.4. Plus, we have to do the parallel time. And no matter how much you break up a chunk of time, it's never going to take 0 time. So the answer to this is it's impossible. There's no solution. There's no way to get this much speed up. That was one of the more applied ones. You should discover that doing the math. If you told me something along the lines of, well, you can't, the math doesn't check out, then you get full credit. Number 8, finish the for loop. This is your homework. I added the C variable to this so that it is slightly different. You're adding into the C instead of into the A. But otherwise, this was your homework, and I've gone over the solution to this many, many times across group studies, individual questions. I think we did it in class even. So that's what you're being asked. And fundamentally, the problem here is we're going to create threads. We're going to call this vecadd function. This vecadd function is just a wrapper function. It unpacks the void pointer, which is one of these structs, into the arguments of vecadd. Now, vecadd does not have to be changed to make vecadd parallel. If we want to split up vector addition into equal chunks and do them in parallel, we don't have to change vecadd at all. We just have to call vecadd differently. Usually you call vecadd like this. You give it A, B, C, and you give it N. That's how you do it sequentially. Our goal is to tell vecadd not to do all the work on the same thread. We want to break up our call into multiple threads. We want to break up the array A into 3 pieces if we have 3 threads, and we want to do each of those threads individually. So each thread gives vecadd a different set of arguments to do their chunk of the array, and the same is true for B and C. So what does that mean? That means that our code down here, our goal clearly is to just pass an argument to pthread create, the correct argument to pthread create. Now we were given an array of these vec probs. And our loop here, of course, is counting the number of threads. So in pthread create down here, in pthread create, our goal is just to give it this V array, the correct element. So this part is pretty easy. We just want to give it the address of V at I. The ith element of V, the ith set of arguments. Each thread has its own set of arguments. This is the ith set of arguments. Now our goal is just to fill this in right. We want the correct values in here. If we look at the struct, it has 4 elements. So we say V at I dot, and then each element. So dot A, dot B, dot C, oops, and what is the last one? Dot N, I think? Or dot size. Let's just go ahead and erase this properly. Dot C, dot size. That's what these are what we want to fill out. If we were going to do this sequentially, then it would just be A, B, C, and N. But we don't want to do it sequentially. We want to break it up across T. And as we've discussed, that just means we want to offset each chunk of the array and have each thread give a chunk of that to vecadd. The way we do that, we tell vecadd where to start, and we tell vecadd how many elements to go through. So our goal is that for I equals 0, you tell vecadd to start at 0 and go to, let's assume each of these chunks is 50. So you tell it you want it to go to 50. And then for thread 2, you want to start at 50 and go to 100. And then for thread 3, you want to start at 100 and go to 150. So to do that, we say instead of just giving A, we give A plus some offset. Let's think about I. When I equals 0, we want it to be A plus 0. We want it to just be A. When I equals 1, we want it to be A plus 50, because we want to start 50 elements later. And then for I equals, for the next one, of course, we want it to be A plus 100. Well, let's think for a second. We don't know what that 50 is. Let's come back to N, or to A. Let's look at the size real quick. Size tells you how many elements are in your array. Well, we know we have n total, and we want to split this up over t threads. So size can just be n over t. Yes, there's an odd condition if the n is odd, but we're not going to worry about that. Oh, well, this is the offset. This is how far we go. But actually, the place that thread 1 stops is the place that thread 2 needs to start. So we can use that. So we can do a plus n over t to tell us where in A we need to start. But there's something missing. If we do this, this is going to be a plus 50 for this, and a plus 50 for this, and a plus 50 for this. We need to use I somehow to tell us what to do. And all we really have to do is multiply by I. A plus I times n over t. Let's say let's say t, the total number of t equals 3. Let's say n equals 150, like we discussed. That means a plus 0 times 150 divided by 3 is 50. A plus 0 times 50 is 0, so it's just a. When I equals 1, it's a plus 1 times 50 over, or 150 over 3. So 50, we'll just write 50 here. A plus 1 times 50. When I equals 2, it's a plus 2 times 50. We want to start at 50. We want to start at 100. That's what this is doing. It's just setting up the outcome. It's offsetting. You're setting the starting point here, and then you continue n over t elements, and then that's where you want the next thread to start. So the overall solution, if I clean this up a little bit, is that, the B and C arrays work the same way. So overall, you want A plus I times n over t, and likewise, you want B plus I times n over t. Likewise, you want C plus I times n over t. This maps to your array. This tells each thread to only do a third or a fourth or a fifth of the work. We want to make sure we tell the size too. Not only do we want to start in the right place, we want to end in the right place. And so the size tells us where to end, or it tells us how many elements to go after the starting point. So that's the solution to this one. Again, this was in your homework. We've gone over this several times. I would consider this one to be a relatively simple problem because we're not doing advanced issues. We're not doing crazy setups. We're evenly dividing work. So you really want to understand this problem because this is really the minimum kind of problem that you want to be able to do with parallelism. All right, so then 9 and 10 are just about parallel task graphs and schedules. So you can refer to the entire set of parallel task graph slides, and I'll show you real quick. They are in a directory in Canvas labeled Slides PTG Theory. And all of them are in here, and the extraction, the scheduling, the metrics that we use to classify these things, those are all in here, and particularly the ones that say scheduling and PTG, and redesigning PTGs. These 4 contain all of the relative information for what I'm about to walk you through. And again, these were homework problems, so I really expect you to have had practice on these before. So real quick, the width is number of elements that could possibly, the max number of elements that could possibly be executed in parallel. Well, how do you execute them in parallel? How do you know they can be executed in parallel in your PTG? The answer is they have no dependencies at the same time. We've discussed before that realistically you need to try every combination if you want to be 100% correct, but the problems I give you The solution tends to be somewhat straightforward, and you don't need to do all that. You just need to work top to bottom. For this particular problem, let's take a look here. Actually, let's finish going through the metrics. So work, again, is total processing time, or sum slash total. It's the sum of total processing time for each task. Critical path is the longest path by time. And then the elements are just going to be whatever nodes those happen to be. The actual critical path is the list of nodes. The length of that path is the sum of the time of the nodes in the critical path. So let's step through this problem real quick. All right, so width. The key with width here is that obviously it can never be more than the entire set. So you'll never have a width of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You'll never have a width greater than 10. When we start at the beginning of time, no matter what schedule we pick, we have 3 nodes available to schedule, E, J, and D. That means width is at least 3. It can't be 1 or 2. We started with 3. If you finish E, then it takes you to G, and that doesn't actually improve your width at all. You still have 3 elements. Likewise with J and D, they both point to 2 elements, but we have to kind of resolve them first. So it's possible we pick up some width from J and D because they have more children. They have more than 1 child. So we could go ahead and execute J and D. And it's difficult for me to illustrate that, although perhaps I can draw. Yeah, so if we go ahead and wipe these 2 out, then what does that give us? That gives us, oh, I actually misspoke. Sorry about that. I got ahead of myself. Let's look very carefully. The starting width is actually 4 because of this H. And so H here, E, J, D, H is going to give us 4. And again with H also has 3 children. So it's possible H could unlock new nodes too. If we finish these 2, J and D like we were discussing, then that could unlock C. And sure, we could finish G, but finishing G, J, and D is only going to unlock C. We're also potentially going to unlock F, but only if we finish H. So as we go through this, you could mark out H if you wanted. You could also mark out we'll leave C alone for now. Or you could even go ahead and mark out C. It doesn't really matter. As you proceed through this, you will have unlocked F because all of its parents are finished. You will unlock I because all of its parents are finished. But we've actually decreased the number of nodes we have to schedule at the same time. Sure, each of these had multiple legs, so they could have turned into more tasks, but actually J and D are parent to the same nodes. So really, you've got 2 nodes that you stand to unlock, and you used 2 nodes to unlock them. You didn't gain any parallelism. Likewise with H points to a child of C. So this is you need to finish 2 nodes to unlock 1. You need to finish 2 nodes here to unlock F. And then the best you can do once you're all the way down here is, sure, I is also done. If it will let me mark it. I is also done. But all that gives us is B, A, and F. So realistically, your width, your peak parallelism happened at the very beginning of this problem. You started with E, J, D, and H, and you never really unlocked more. There are no nodes in this that have more children than they have parents, which is really limiting the width in this problem. So if you marked through a couple of cases like I just did, then you probably ended up back at 4. And that is the solution to this problem. So if you showed your work on that, then that's great. And, well, you got the width right. The work, you just sum up all the nodes. So, you know, let's move a little bit of this. So you do 2 plus 2 plus 3 plus 5 plus 3 plus 4 plus 4 plus 1 plus 1 plus 3. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes. And so then you get 4, 7, 12, 15, 19, 23, 24, 25, 28. You should have gotten something like 28. I'll double check that number or I double check that number when I grade your exams, but loosely that's what it should be. And then critical path in this problem, it's a little tricky for me to draw it, but you want to look for the longest path. So that means you want to add up the numbers for the paths you think are likely and see how big you get. So let's look at this very long chain. You get 2, 4, 7, 11, 12. Okay, that first path is 12. We'll go ahead and write that down. We already know a better path because we could go down here and go to A. That's going to give us 12 again. Or we could go to F, and that's going to give us 15. So that's even better. So E through F. What else could we have? We could have this 3. Probably not going to be any better because you could do 3, 6, 10. This is just 11, 11, 13. So that's not any better. We could start at this 5. 5, 8, 12, 13, 13, 15. That makes me look like I miscounted. 5, 8, 12, 15. And this one was 2, 4, 7, 11, 14. So previously this had only added up to 14, but now we found it's 15. And then, of course, when you're doing this on your exam, you should write these down. It's a little easier than doing them in your head like I'm doing. And then we only have so many other paths we can take. You can take D from 5 to 3, that's just 8. You can take H down, that's 4 plus 3, that's just 7. That's just 5. That's just 4 plus 4 plus 3. That could be an interesting path, but that's just 11. And there's really not that many other paths you can do. You can start at any arbitrary place and you're going to get lower numbers if it has parents. So you started all these routes, we evaluated all the paths. I found 15. And so that's really the technique here, is you try the different paths. And so then the correct answer for that, since we think it would be this starting at D, you do D. Of course, 5 is bigger than the 4 that's contributed here, right? You have D, C, I, F is your critical path. D, C, I, F with a length of 15, and that'll get you what you want. And so then that was the answer to that question, and then make a schedule pretty. Okay, so I went ahead and set this problem up for us to walk through right here. So we have our Gantt chart. This is time. This problem asks us to make a schedule, assuming we have 3 cores, 0, 1, 2. The scheduler has one, it wants us to use longest process first scheduling. And in addition to that, there's one additional constraint. It says that it wants us to prefer to schedule the longest available task to the lowest number available core. All that means is if core 0 is available and one task has 5 seconds and the other task takes 10 seconds, you should schedule the 10 to 0. And really that's more for me to make sure that you give pretty consistent answers. It makes it a little easier to grade. So with that in mind, we can go ahead and jump in. I've already listed our starting units here. We need to start with E, J, D, H, just like we did for the other problems. These are the ones with no dependencies at the beginning, so they're available to schedule. We want to pick the longest one and assign it to core 0. The longest one, of course, is D, and it takes 5 units, so let's go ahead and schedule D. 1, 2, 3, 4, 5. Second longest is going to be H, and that goes for 4, so we'll schedule that till here. Third longest is J. And so we put J here. And then our hands are tied, we're out of cores. So we have to fast forward the clock. The first task to finish is going to be J. So we can mark J out. Now J doesn't unlock us any dependencies because J's children both have more dependencies. C still depends on G, F still depends on D and H. So even when we finish J, it's not going to help us yet. But when we finish J, we do have one task available. And that's the task we didn't schedule, which is E. So we can go ahead and schedule E here. Okay. Now scheduling E is going to go for 2 time steps. But once we schedule E, we're out of tasks again. We don't have anything else we can schedule. So we'll look at H. We'll finish H. H's children, I and F and A all have more dependencies, so that doesn't help us. We're still waiting on, even though this is cleared up, this is cleared up, this is cleared up, this is cleared up, this is cleared up. This D still exists, this I still exists. We've almost cleared up C though. And so the next event to happen when H finishes is it looks like we're just going to have to wait because the only nodes available are already on the board. E and D are still running, and there's nothing else with no dependencies. When D finishes next, let's double check real quick. J has a length of 3 and E has a length of 2, so it should actually finish at the same time as D. That's why it's very important to be careful when you draw these timings, is you want them to line up. So E and D are both going to finish at the same time, and then all of our processors are going to be free again. So we will be able to schedule something new. So let's go ahead and finish them. H is done, J is done, E is done, D is done. And we're going to be here. When we're here and G is the next available task, is it the only available task? I think so, because again, we didn't free anything up with any of these others. Although with D, notice we did mark out this and this dependency. Oops. Well, it's getting hard to draw. Okay. So I marked out these 2 dependencies. So F is still in the back of our mind, but it's not going to get there until we have I. And that's actually true for all these nodes at the bottom, right? All of them depend on I. So really, we just have to work our way down this chain. So the current available core is going to be 0. There's only one task available to us, and that's going to be G. So we go ahead and schedule G for 2 units. When G is finished, it unlocks C, and nothing else, right? C points to nothing else. So we schedule C. 1, 2, 3. When we finish C, it unlocks I and nothing else. So you get 1, 2, 3, 4. Yep. We'll put I in here. And then you get B, A, and F all at the same time. And you just want to schedule those in order. And the order is F goes at the bottom because it's the longest. And then the other two just go on top of it. And for that one, they're both 1, so in either order. A, B, and you're done. So that's that problem. This is the preferred schedule. I think the only variance here is A and B can be flipped. But most of this graph is sequential because, again, if we roll back all this nasty marking we've done, all of these nodes at the bottom depend on this I. And all the nodes up here, these are all free at the beginning. This kind of chunk here is free. But then after you do that, everything at the bottom depends on I. I depends on C. C depends on G. And so you end up with a stretch like this. All right. And so that's a good 10, 15-minute problem. That's why it was organized that way. Let's go ahead and move on and do the last one. So this last one is the more generic form of the task graph, the more real-world version of the task graph. It just asks us draw a PTG for the code below. Illustrate dependencies. You should exclude the transitive dependencies. And then answer the metric. So the first thing we have to do is draw the graph. Now, again, I want to highlight the key things. This tells you not to include transitive dependencies. And I've discussed this several times as people have asked, and we've gone over this over time, but after the first set of problems, you start to realize that first, if you know read after read is not a dependency, then you start looking for writes. There has to be a write involved. There are 2 writes here, sum, and y equals I. I know I said 3, but you do sum twice. So the sort of proper way to do this, if we follow the guides that we were given, 1, we're going to go through this step by step, and 2, I'm not going to write any of the dependencies for a at I, j, or x, because we never write to those values, so it's impossible for them to generate a dependency. All right. So we have a task which in our discussions we've referred to as a pre-task, called I equals 0 pre. The interesting piece about this pre-task is it has two writes. First, you have write to sum. Actually, for the pre-task, you just write to sum. The only thing you do in the pre-task is sum. Okay. Then you have I equals 0, j equals 0. When you do this, y equals I, we'll start at the top. So sum plus equals aij times xj. Again, the interesting thing here is we write to sum. And so we write to sum. And that's really it for this task. This yi is a post task. And so we can draw it that way if we want to. We loop through each of the j's. So we do I equals 0, j equals 1. When we do j equals 1, you write to sum. That means these two are dependent. We write after write sum. And you'll notice we have that here too because we write sum up here also. In fact, for the sake of argument, we should probably just go ahead and move this task down here. We'll move the pre-task down here. We're going to write to sum. And then, for I equals 0, j equals 2, we write to sum. You're going to notice this keep happening. So we take this to infinity, or at least to n, I equals 0, j equals n minus 1. You still write to sum, you still depend on the sum right before you. And then finally, the post task, once we're out of this loop, y equals I equals sum. So I equals 0 post. Y at 0 write sum read. And that's the end of the inside of the J. It just builds one long chain. What's interesting then is if we go on and we do I equals 1 pre, we're going to write to sum. Notably, we depend on the sum that we just read from. This happens first if you execute this sequentially, right? We do y equals 0 equals sum, y at 0 equals sum. Then we loop back around and we reset sum. That means we need to read the value from sum before we set sum back equal to 0. So we depend here. And then this pattern is going to repeat. So you're going to end up with the same pattern all the way down to n minus 1, I equals n minus 1, all the way to j equals n minus 1. And this is generally your task graph, and if you drew this, that's good. If you zoom out 50,000 feet, your task graph looks like this. Whoop, and then loop back, and then loop, and then loop back, and then loop, and then loop back, and then loop. And you find we zigzag through the whole thing. We have to go all the way to the end of one chain before we can start the next chain, before we can start the next chain, before we can start the next chain. So, for our questions, what is the width? Well, the width is 1 because every node depends on the node before it. Work is going to be n squared. Why? This makes a square. It's n by n, and you have to do all the nodes. It's n squared. The critical path, the actual critical path, is the whole thing. This might be the only time I've given a critical path where it's hard to draw the critical path because you have to keep track of these arrows. But it's the whole thing. You do each row sequentially in order. And so that means the length of the critical path is also going to be n squared. Every node is on the critical path. And then, well, that's the rationale, right? Every node is on the critical path because of this dependency. That's why it's everything. Can we expose more parallelism? Yes. Remove sum. If you get rid of sum and you just use y at I directly, then you break all these dependencies. You can erase this sum variable, replace it with y equals I, and they will not collide between rows. So if we erase, if we're able to remove that, that's going to change our picture so that this, each one is going to be, each row, each I value is going to be independent, and you can do each I in parallel. And that changes all your metrics. That makes your width n. That makes your work stay the same, but it makes the critical path also n. Which means you're getting a lot more out of, right now you're not getting any parallelism. That's going to give you a very good high degree of parallelism. Okay, and really that's the end of the exam. So those are the key ideas. My advice is, again, go back and study these problems, go back and study your homeworks. I think you've seen everything on here before. And so that's my advice. So thanks for watching, and we'll see you in class.